Hello guys, I'm back after a long time. So let's pick up where we left off. We had finished Thevenin's theorem, so we'll start with Norton's theorem today. First, let's just do a quick recap of the Thevenin's theorem. So the Thevenin's theorem was simplifying any circuit into a circuit with a single voltage and a single series resistor. Okay, so the circuit was something like this. There would be a voltage source. This is ETH, Thevenin's voltage. Then a series resistor. So this would be RTH, Thevenin's resistance. And just any load here, RL. Okay, so this was Thevenin's circuit, simplified Thevenin circuit, or equivalent Thevenin circuit. Now we will start with Norton's theorem. Norton's theorem is the same as Thevenin, but this time we're simplifying the circuit into an equivalent circuit with a single current source. So we would have an IN and a single parallel resistor, so RN. Okay, remember this time it's parallel resistor. This is parallel, while RTH was series. That's the key difference. And also this is a voltage source I, and this is a current source I, and this is a voltage source. So an equivalent equivalent Norton circuit would look something like this: a current source IN, and then a parallel resistor. This would be RN, and the load in parallel with it. This would be RL. Okay. Now let's look at the relationship between Thevenin and Norton and the theorems, not between the actual people. Okay. So Rn is equal to RTH. Okay. We will see later that we use the same steps to find these two resistances, so they are the same. Okay, we can write them interchangeably. And the other key relationship is that ETH is equal to IN and RN. Okay. So with these two things in mind, we can interchange between the Thevenin's equivalent circuit and the Norton's equivalent circuit. So technically we don't have to learn both the theorems if we like thinking in terms of voltage. If you like thinking in terms of voltage, you can learn the Thevenin's theorem, and if you like thinking in terms of current, you can learn the Norton's theorem. Okay, and from here we can also calculate IN if we have ETH. So if we have ETH, then IN equal to ETH over RTH. And remember that RTH is the same as RN, right? So we can interchange between them very easily. Now let's take a look at the steps of solving the Norton's theorem. So we have a simple circuit here. Again, remember the blue part, the shaded area, is where we will apply the Norton's theorem. And this RL will just stay as it is. Okay. And we will find the Norton's current for this marked terminal here. This will be IN. IN will be passing through here. Okay, so the first step is to find RN, Norton's. We find Rn the same way we found RTH, so same as RTH. Now how did we find RTH? If you remember from the previous video, which was a long time ago, we removed all the sources and replaced the voltage sources with a short circuit. So this E here, we will replace it with a short circuit, and the resistors will remain the same. Okay, and the load part will just remain open. So this is R1, 3 ohm. This is R2, 6 ohm. Okay. And it comes in like this. Okay. So we can see here that R1 and R2 is getting split. So R1 is parallel to R2. So that's Rn. Rn is equal to R1 parallel R2. So 3 parallel 6, and that equals 2. So 2 ohm. Rn is equal to 2 ohms. Now step 2 is calculate not ETH, calculate IN. The first part of calculating IN is the same as the first part of calculating ETH, which is replacing all the sources. So let's redraw the circuit by putting the source back. We had a voltage source here. It was 9 volts. And the resistors will remain as they were. And this is the open load terminals. So this was R1, 3 ohm. And R2, 6 ohm. Okay. Now the important part is, for IN, we will calculate the short circuit current. Okay, so IN is basically the short circuit current. Let's write that down. IN is the short circuit current. Circuit current across the open load terminals, which are these two. Okay, so these are the load terminals. And the current across this will be this. So this is IN. Okay. Now we start from here, plus minus. If we look at it, the current will go across this, and then here will be a junction. Now, since this is short circuited, current always follows the path of least resistance. So there is no resistance here. So all the current will go here. There will be 0 current here, okay? 0 ampere this way. So all the current that's produced here after will go through here. So by analyzing the circuit, we can see that R1 will be in series with the short circuit current passing through here, and this resistance is ignored, right? So Norton's current IN equal the voltage we have here, so that would be E, or 9 volts, over R1. Okay, because R2 is ignored because there's no current passing through it. So that would be 9 over R1, 3 ohm, equal to 6 amperes. Okay, so that is the short circuit current through the load terminals, and that is the Norton's current. So our equivalent Norton's circuit would look like this. We have a by the way, this arrow will depend on the direction of the voltage source here. So the voltage source here had the plus on the top, so the arrow will be pointing to the top, to north. And if plus was here, plus was down here, then the arrow would be down, going like this. So this would be our IN, which is 6 amperes. And then the Norton's resistance in parallel. So this is Rn, which is 2 ohms. And then we have the load resistance, which is just as it was. So this is our final equivalent Norton's circuit. Now let's solve another Norton's theorem circuit. So again, step 1 is remove all the sources. Now we have a current source here. That won't change much, except it will be a short circuit. Open circuit. So here we have the open circuit, and this will also be open because of the load terminals. So this is R2, 4 ohms, R1, 5 ohms. That's it. So what's the equivalent circuit here? We have R2 with only one terminal in common with R1, right? And this is all open. So we can see that Rn is equal to R2 and R1 in series. So R2 plus R1. And it will actually be like this, Rn this way. So we should write it R1 plus R2. R1 plus R2 because in series. There's no change. So there's no junctions anywhere, so it's series. Now R1 is 5 ohms plus R2 is 4 ohms. That's 9 ohms. Therefore Rn equal to 9 ohm. Okay. Now step 2 is replacing the sources. So we have a current source here pointing to the right. Okay. Now this is R2 and this is R1 and this is 10 amperes. So what we have to do is place a short circuit here. Okay, and this would be IN. Now this circuit looks a bit complicated. Is R1 and R2 in series or parallel? No. Okay. Pause the video and try to guess whether R1 and R2 is in series or parallel. Now I hope you guessed right, but we don't have to guess. We can check it by redrawing the circuit. So let's draw this as a separate part of the circuit. Okay, so we have R1, then we have the source pointing downwards. We basically flipped this here. Okay, so this is R1 and this is 10 amperes. R1 was 5 ohms, 5 ohm here, 4 ohm here. So this is 5 ohm. Okay. After flipping this, all we have left is one extra branch, which is R2. So let's draw that extra branch here. Okay. So this is R2, 4 ohms. Now we have a connection R2 with the top of R1 and 10 ohms. So the connection goes here. But we can just draw it here to make it look simpler. But they're the same thing. So let's remove this and put the connection here. Okay. So here we have a junction. And we have another connection with the open terminal. Let's name this B and this A. So this is B because R2 is connected to B. And this, let's say, it's connected from, again, in the middle of R1 and 10 ohm. But we can just write it in one side. We can draw it here or here, doesn't matter, they're the same thing. So we'll draw it with R1 for simplicity's sake. And here we have A, okay? So this and this. Now if we connect them, let's connect them with another color, blue. So if we connect them, that is IN. And the current is going this way. Okay, because following the direction of this. So this comes from here and goes down from here. So this is IN. Okay, now see, is R2 and R1 in series or parallel? Easy to spot two common points, right? Because this is connected. So two common points means R2 and R1 are in parallel. So here are their parallel. So let's just write RP. RP is equal to R1 parallel R2. So R1 is 5 parallel 4. That's 1/5 plus 1/4. That's 2.22 ohms. 2.22 ohm. Okay. Now try to guess how we will find IN. Okay. Pause the video and try to guess. If you guessed current divider, then you are right. Because R1 and R2 is in parallel and IN is the current that is in series with R2. So the IN is flowing through R2, right? That's IN. But it divides here. So IN is not the same current flowing through R1. Since IN is the divided current, we can use the current divider and just write it like this. IX, or we can just write IN. It's easier to write it IX. It's easier to remember. So I remember it like this. IX RX equal to IP RP. I don't write T here because total resistance would mean the resistance outside the parallel circuit too if it was here. To remember it, I just write it like this. It's easier to remember. IX equal to RX, IX RX equal to IP RP. Now IP here is the total current. It's always the total current. So you could write IT equal to 10 amperes. Then RP is the parallel resistance, parallel equivalent resistance. Resistance, which is 2.2 ohms here. 2.22 ohms. IX is the current we will find. So IX equal to IN. Norton. Equal to what? And RX is the resistance across which IN is flowing, which is R2 here. So equal to R2 equal to 4 ohm. Okay. Now we will just rearrange the formula. We need IX, or we can just write this equal to IN equals IP RP over RX, or RX we can write that as R2. So what's IP? IP is 10, RP is 2.22, and R2 is 4. So that equals 10 into 2.22 over 4. 5.55 ampere. So therefore IN is equal to 5.55 ampere. We have everything. Now we can just draw the equivalent Norton circuit, which will be current source. Now which direction will the current source be? Same direction as the original source. Original source was pointing downwards. So current source will also point downwards. Okay. And we have the Norton's resistance Rn, which is equal to, what's our IN? IN is, so here IN is 5.55 ampere. Just write IN 5.55 ampere, and Rn was 2.22 ohms. Rn is 2.22 ohms, and we will have RL here. The value of RL does not matter. Okay, so that's the equivalent Norton's circuit. Now let's do one more example. Now this circuit looks positively scary, but it's not really scary because all of this is just RL, okay, because it's after the terminal and outside the shaded area. And we have to apply Thevenin only here, okay, across these parts. Okay. So again, step 1, remove all the sources. We have a resistor here, and this will be short-circuited. And then we have, we go down. The current source will be open circuited, yeah. And we have another resistor here. And then just the load terminals. We can write A, B. So R1 here is 4 ohms. And R2 is 6 ohm. And Rn comes in this way. As we can see, they divide here. So R1 is parallel to R2. And that's Rn. So it's R1 4 parallel to 6. That's 1/4 plus 1/6. 2.4 ohms. Therefore, Rn is equal to 2.4 ohms. Okay. Now, step 2, replace all the circuits. All the sources. So we have a R1 4 ohms. Then we have a voltage source, which was 7 volts, and E1. And then we have a current source here, pointing downwards, and 8 amperes. I 8 amperes. And then we have R2 6 ohms. So this is R2 6 ohms, and then the load terminals A and B. Okay. Now we have to find the total resistance here. Now this again looks scary. How do we do that? How do we find the equivalent resistance here? We use the superposition theorem. Okay, now remember what the superposition theorem was? Superposition theorem is when we have multiple sources. When we have multiple sources, we calculate the effect of each source individually. That's the superposition theorem. Now this effect can be calculated in terms of current for Norton's theorem. So we will find IN for 7 volts and also IN for 8 amperes, these sources. Okay. And we replace voltage sources with short circuit, current sources with open circuit. So let's apply superposition for the 7 volt voltage source first. So we will have the same circuit, except that the current source will be replaced by an open circuit. Okay, and then the load terminals. So we have 4 ohms here, we have 6 ohms here, and this is E1 7 volt. So what's the IN here? Let's write IN 7 volt. We can see that R1, it's in series with R2 because it goes straight, and go down. But we are calculating IN, so we will short circuit the load terminals. Okay. Now what happens after a short circuit in the load terminals? It's still series, but since current follows the path of least resistance, and there will be nothing flowing here, so this will be 0. This way will be all the current produced. So IN 7 volt, everything is here. Okay. The only resistor here is R1 4 ohm. So IN 7 volt equals what? E1 over R1. So that's 7 volts over R1 4 ohms. 7 divided by 4. We have 1.75 amperes. Okay. Now again we will, so that's our one. Now we need another one for 8 ampere, the other source. Now we will replace the voltage source with a short circuit. Okay. Then we will bring in the current source pointing downwards and 8 ampere. 8 ampere. This is R1 4 ohms. And we have the other resistor, which is R2 6 ohms. And then the load terminals A, B. Okay. And then we will short this. Okay. Let's not write IN here. So after I short this, what will be the current flowing? Will anything flow through 4 and 6? Pause the video and guess. No current will be flowing through 4 and 6. Why? To understand that, we can redraw the circuit again. Now look, 4 and 6 are in two sides of I, right? So if we bring I to the left side or to the right side, nothing changes. It's the same, because R1 and R2 are essentially in parallel now. So let's draw the source to the left side. Okay. And we have R1, we have R2. This is 8 amperes. This is R1 4 ohms. And this is R2 6 ohms. And then here we have the short circuit terminal. Okay. Wait, it's not that way. It's gonna be the other way. And this too will be other way. Why? Because the current is going downwards. So current goes here, then here. Now it has a choice here. Two paths. Which path will it go to? This path has 4 ohm and this path has 0 because it's short circuited. So it will obviously go this way. And this will also get ignored because this has 0 resistance. It's path of least resistance. So current goes this way and then up. Here will be 0 and also here 0. Okay. So whatever current we have at the source is the same current we will have at the short circuit. So IN here is IN 8 ampere equal to 8 ampere. So what's the total Norton's current? IN equal to IN 7 volt plus IN 8 ampere. IN 7 volt was 1.75 ampere. So IN 8 ampere is 8 ampere. So 1.75 plus 8, that's 9.75. 9.75 ampere. Okay. Now we can draw the equivalent Norton circuit. So that's a Norton's current facing downwards. Why? Because the source was facing downwards. And then we will have a resistor in parallel and the load terminals are RL. IN was 9.75 ampere and RN, what is RN? RN was 2.4 ohms. 2.4 ohms and RL was doesn't matter.